reaction mechanisms. Most reactions occur in several steps. And the chemical equation that we're familiar with only shows the substances that are present before the reaction starts and the substances that are formed by the reaction and remain afterwards. It doesn't show any of the intermediate products. So a reaction mechanism is a series of individual steps by which the reaction actually occurs. So each elementary step represents the exact species that are colliding in the reaction. So if we look at hydrogen and iodine monochloride, in the first step, hydrogen collides with ICl and makes hydrogen iodide and hydrogen chloride. In the second step, hydrogen iodide connects with another ICl to form HCl and I2. So this guy here, this HI, is an intermediate. It's formed during the reaction and then it gets used up again. It gets formed and used up and formed and used up. So at the end of the reaction, we don't see it. That's a reaction intermediate. They're formed in one elementary step, consumed in another. The individual steps for the mechanism have to add up to the overall reaction. So the reaction mechanism, complete detailed description at the molecular level of what's going on, shows which individual collisions occur. Chemical kinetics help us to determine the mechanism of the reaction. We can measure the kinetics of the overall reaction and then work backwards to write a mechanism that's consistent with those kinetics. Identifying the reaction mechanism for a particular reaction is not a simple matter because you can't just zoom in and see what they're doing, right? So these elementary steps are characterized by what's called the molecularity. How many molecules are involved? So unimolecular, one molecule. You just have one molecule reacting, making stuff. Bimolecular, you could have two of the same molecule, they're colliding and making products, or you can have two different reactants, but you have two molecules involved. There are termolecular steps that involve three particles colliding simultaneously, but those are really rare. Because think of the odds of getting three particles to collide in just the right orientation. It doesn't happen very well. For elementary steps, and for elementary steps only, we can identify the rate law from the equation. Because the elementary step actually describes what the molecules are doing. Students like this, and then they try to use it on all the equations. It only works for elementary steps of a mechanism. Okay? We already learned how to do the other thing. So, molecularity of 1, we have a first order rate law. We've got A and A that have to collide. They're two of the same. Then we've got Ka squared. Two different ones, and then it's going to be Ka times B. And so what this ends up being is the rate constant times the molecule raised to the coefficient. But you can only do it for elementary steps. The molecularity is the same as the overall order. So as you mentioned in the video, usually one of those steps is a lot slower than the others, and that's called a rate determining step. It limits the overall rate of the reaction and determines the whole rate law. We have an illustration here of some work being done on the freeway. cars are coming up fast this way, and as soon as they get around this thing, they zoom off at the speed limit or higher, right? But here, where they have to all merge together, everything slows down, right? And so you can't get through this stretch of highway any faster than these cars are going. Does that make sense? So the rate limiting step is a little bit like a bottleneck in traffic. So for this reaction between NO2 and carbon monoxide, the experimentally determined rate law is this: the rate constant times the concentration of NO2 squared. Could this possibly be a single-step reaction? Well, what about the CO, right? These guys have to run into each other at some point. That doesn't show up at all in here. A possible mechanism for this is that the two NO2s run into each other. That's where we get this. And they make something different. And then this NO3 collides with the CO and makes the actual products. The rate law for the slow step is what ends up determining the overall rate. Because once it gets through here, it doesn't matter how fast this is. It's faster. And so this is going to limit the rate of the reaction. So here, a slow first step, from that elementary step, we can figure out what the rate law is. So in that reaction, the first step has a higher activation energy. So its rate constant is smaller. The first step predicts the overall rate and has the same rate law as the experimental data. Because once you get over this hump, then this part happens really easily, and you get to your products. So these are conditions for a valid mechanism. The elementary steps have to add up to the overall reaction. The rate law predicted by the mechanism has to be consistent with the observed rate law. The rate law for the reaction is determined by experiment. And that is the rate law for the reaction. What we come up with from the mechanism by looking at the the slow step, has to agree. Now, that doesn't, if these two things are true, that doesn't prove that that's the correct mechanism, only that it's possible. You can rule them out, but you can't prove them to be true. You got to do a bunch of other stuff if you want to prove it. So when we have a fast initial step, then the rate law that we get predicted by the rate limiting step might have reaction intermediates, and we can't have reaction intermediates in our rate law for the overall equation. So if the first step is fast enough, it may actually establish an equilibrium. So the rate of the forward reaction is equal to the rate of the reverse reaction. And here's an example. So here we have a fast first step, a slow second step, and a fast third step. So show that condition 1 is met, elementary steps add to the overall reaction. So to do that, this is just like doing some Hess's law stuff. We're going to add these. And you can cross off things that appear on both sides, like these guys. And anything else? H2, H2. Oh, I think that's it. So then I'm going to write down what I've got here. Nope, these guys. Oops. The N2O2, R2D2. So 2, no, plus, and we've got 2H2. And that's going to make 2H2O and N2. So these steps add up and give us the overall reaction. See how that works? For condition 2, the rate law predicted by the mechanism needs to be consistent with the observed rate law. So what we can do here, because for this slow step, it's going to have N2O2. And we can express that concentration in terms of the reactants of the overall equation. Let me make sure I'm not skipping something. Nope. So we can say that the concentration of NO squared times its rate constant is equal to, let's call that KF and KR, N2O2. This is telling me this is at equilibrium. The rate of the forward reaction is equal to the rate of the reverse reaction. Because it's an elementary step, I can write rate laws using coefficients. So the forward reaction is going to be NO squared times the rate constant. The reverse is going to be N2O2 times a different rate constant. So what I want to do is I want to find an expression that gives me N2O2 in terms of something else, because I can't have this showing up in my final rate law. So the rate law for our slow step here is going to be what? Rate equals a constant times. Yeah, H2 times N2O2. Coefficients of 1, so exponents of 1. This can't be the overall rate law because that's an intermediate. So I'm going to take this equation and rearrange it. So divide that out. Now I can take this and put it in for that. So the rate is equal to my rate constant times H2 times KF over KR NO squared. You okay with that? We have 3 different rate constants here. We don't need to know these individual rate constants. We can just pull them all out and call them K prime. Now, is that the same rate law that they gave in a previous slide? Oh, good, it is.